Hello, my name is Nkechi Ezenwa. This is a course project for Machine Learning Foundation for Product Managers in Coursera. Like it says here, the project will be building a model to predict the electrical energy output of a combined cycle power plant, which uses a combination of gas turbines, steam turbines, and heat recovery steam generators to generate power. We have a set of 9568 hourly average ambient environmental readings from sensors at the power plant, which we will use in the model. These are the overview of what will be used, the column data that consists hourly average ambient variables, relative humidity, exhaust vacuum, net hourly energy, electrical energy output. So in completing the project, we'll be looking into some modeling process, which will include determining which possible feature we want to use in the model, the splitting of data, then training the set to determine the validity strategy for comparing different models. Now let's go to the project. Now, to build a predictive model for the electrical energy output of a combined cycle power plant using the provided dataset, we need to follow these steps. This is the provided dataset that we'll be using to build this. First, machine learning approach and output metric. Given the nature of the data, this problem is best situated for a regression approach, as we are predicting a continuous variable. The net hourly electrical energy output for evaluating the model's performance. Common metrics in regression tasks include mean absolute error, mean squared error, root mean squared error, R squared coefficient for determination. Next, feature selection and algorithm choice. Features to consider: temperature, ambient pressure, relative humidity, exhaust vacuum. These features directly affect the power output of a combined cycle power plant. Now, we'll have to look at the other algorithm to consider, which is linear regression for a base model, decision tree regression to capture non-linear relationship, random forest regressor for a more robust model through example learning, gradient boosting machine, e.g. XBoost, for potential better performance at the cost of increased complexity, data splitting and validation strategy. Split the data into training and test set, e.g. 80% training, 20% testing. For validation strategy, use either a fixed validation, e.g. a further split of the training set, or k-fold cross-validation to tune and select the best model. Model comparison and selection. Train at least 2 different models using the choosing algorithm. For example, a linear regression model and a random forest regression. And I will experiment with different combinations of features and hyperparameters. Then compare their performance using the validation approach and select the model that performs best on the validation set. The final model evaluation is to evaluate the selected models on the test set using the choosing output metrics. Now, I'll be loading the exploratory file to understand the data distribution to prepare it for the model. like I showed earlier, the CSV file. In the CSV file, we have the data. The data contains the following columns: AT, temperature; exhaust vacuum in cm; ambient pressure in millibar; relative humidity; net hourly electrical output. Next, I'll perform some basic data processing and exploratory data analysis. This includes checking for missing values, examining the distribution of variables, and possibly visualizing relationships between features and the target variables. This step is crucial for understanding the data and guiding our model decision. I'll proceed to this initial data analysis. The initial analysis of the data set reveals several key insights. Missing values. There are no missing values in this data set, which simplifies the pre-processing stage. Statistical data. Correlation. There is a strong negative correlation between temperature, the energy output, and a similar strong negative correlation between the exhaust vacuum. Ambient pressure and relative show positive correlation. Distributions. The histograms provide a visual presentation of the distribution of each variable. Based on these insights, the next step involves preparing the data for modeling. This includes normalizing or standardizing the features, if necessary, to ensure that they are on a similar scale. Splitting the dataset into training and testing. I'll proceed to the data normalization and splitting the dataset. The dataset has been successfully split into training and testing set, with 80% of the data used for training and 20% reserved for testing. The shapes of the split are as follows: training features, testing features, training target, with all the samples seen here. Testing target. I will continue with model training and evaluation. I will use these models as discussed: linear regression and random forest regression. For each model, I will evaluate the performance using stable metrics. Next, to train and evaluate the random regressor, which is a more complex model that can capture nonlinear relationship. The random forest regressor model achieved a root mean squared error. This improvement indicates that the random forest model, with its ability to capture more complex relationships and the interaction between features, is better suited for predicting the electrical output of the combined cycle power plant. Given these results, the random forest regressor will be the preferred model for this task. However, further model tuning and validation, such as hyperparameter optimization or cross-validation, could potentially lead to better performance. Thank you.